Welcome to the We Shall Overcome seminar series conducted by the Physics Department of Sacred Heart College, Thevara. Firstly, I take this opportunity to thank our professor, Dr. Pius Augustine, for giving us this opportunity to understand the need for researching and observing various aspects of physics other than our textbook lessons. Now, let me introduce the members of our group. I myself, Sreelekshmi M, Aleena Maria, Gopika Nair, and Jithin K. Joshy. So once again, I welcome all of you to this small seminar session on thermodynamic process and its application. This short seminar will contain what thermodynamic is, what thermodynamic processes are, and a phase diagram. The four major thermodynamic processes, which is isobaric, adiabatic, isochoric, and isothermal processes, which will be dealt by each one of us. To begin with, what is thermodynamics? Thermodynamics is a branch of physics which deals with the energy and work of a system. Now, this branch of studies was born in 19th century as scientists were first discovering how to build and operate steam engines. Thermodynamic deals only with large-scale response of a system which we can observe and measure in experiments. The small-scale gas interactions are described by the kinetic theory of gases. The methods complement each other. Some principles are more easily understood in terms of thermodynamics, and some principles are explained by the kinetic theory. Thermodynamic process. Now, how does the food stay cold and fresh in refrigerator? But have you noticed, even though the entire inner compartment of a refrigerator is cold, outside or the back side of the refrigerator is warm, in fact hot. Here, the refrigerator pulls heat from its inner compartment and transfers it to the region outside. Now, this is why the back of the refrigerator is warm to touch. So, thermodynamic processes involve heat energy moving within a system or between systems. Now, thermodynamic process is defined by change in the system. It is a passage of a thermodynamic system from an initial to a final state of thermodynamic equilibrium. Now, the initial and the final states are the defining elements of the process. But the actual course of the process is not of primary concern, and it is often ignored. So, a state of thermodynamic equilibrium endures unchangingly unless it is interrupted by a thermodynamic operation that initiates a thermodynamic process. So, today we will be dealing with four major processes and its applications. Isobaric process, adiabatic process, isochoric process, and isothermal process. Phase diagram. A phase diagram in physical, chemistry, engineering, mineralogy, or whatever science, it is a type of chart which is used to show conditions like pressure, temperature, volume, etc., which are thermodynamically distinct phases, which they occur and coexist at equilibrium. There are two major kinds of phase diagrams, a two-dimensional diagram which is pressure versus temperature, and the other one is a three-dimensional which consists of pressure, temperature or volume or any three together. Isobaric process. Now, what is isobaric process? An isobaric process is a thermodynamic process taking place at constant pressure. Like the term isobaric, the word it has been derived from the Greek words iso and baric, which means constant pressure. As such, the constant pressure is obtained when the volume is expanded or contracted, so which basically neutralizes any pressure change due to the transfer of heat. Now, in an isobaric process, when the heat is transferred to the system, there has to be some work done. So, however, even though there is no change in the internal energy of the system, this further means that no quantities, as in the first law of thermodynamics, becomes zero. So the work done in a thermodynamic isobaric thermodynamic process is given by the equation W, which is the work done, is equal to P delta V, where P is the pressure, which is constant, and V delta V is the change in the volume. This is the PV diagram for an isobaric process. The work done by the gas is represented on the PV diagram by the rectangular area under the isobaric path on the diagram. Now, whether the area is positive or negative is dependent on whether the gas has expanded or compressed. The two applications of an isobaric process that I've mentioned here are boiling of a water and hot air balloon. Now, boiling of a water is a very simple isobaric process. So, you have a pot of water on the stove and it is at atmospheric pressure. Now, as the water boils, the steam coming off expands to roughly about 1600 times of that of the water. And there is nothing to contain this steam, so it stays at atmospheric pressure. The next one is hot air balloon. A hot air balloon is lighter than aircraft, consisting of a bag called an envelope which contains heated air. Now, this heated air inside the envelope makes it buoyant since it has a lower density than the colder air outside the envelope. As with all aircrafts, hot air balloons cannot fly beyond the atmosphere. The next process is adiabatic process, which will be dealt by Gopika.
Now we are going to discuss another important thermodynamic process, adiabatic process. Adiabatic process is the process in which the system does not exchange heat with its surroundings. There is no heat flows in or out of the system. So the equation for first law of thermodynamics, delta Q is equal to delta U plus delta W, here becomes delta U is equal to minus delta W. From this equation, it is clear that if work is done by the system, the internal energy of the system decreases by the amount of work, and also if work is done on the system, the internal energy of the system increases by that amount. An adiabatic process is a quick process so that there is no time to transfer heat. In an adiabatic process, system must be perfectly insulated from the surroundings so that there is no transfer of energy as heat occurs between the system and its environment. A reversible adiabatic process is also known as isentropic process because there is no entropy change since there is no heat transmission. Following is the equation for an adiabatic process. PV raised to gamma is equal to constant, where P is the pressure of the system, V is the volume of the system, and gamma is the adiabatic index. What is an adiabatic expansion and what is adiabatic compression? Adiabatic expansion is a situation whereby an external work acts upon a system at the expense of utilizing internal energy of the gas and results in lowering the temperature of the molecule of gas. Adiabatic compression is a process in which no heat is gained or lost from the air and the internal energy of the air is increased. In this process, pressure increases quicker than volume diminishes due to increase in air temperature. Work done during an adiabatic change. Let the gas expands adiabatically from an initial volume V1 to final volume V2, and the corresponding values of pressures are P1 and P2. Work done by the gas integral V1 to V2 PdV. By integrating this value, we get final equation for work done. Work done during an adiabatic process is equal to R by gamma minus 1 T1 minus T2. There are many applications for an adiabatic process. Some are noted below. Adiabatic efficiency is applied to devices such as nozzles, compressors, turbines, pendulum oscillating in a vertical plane, quantum harmonic oscillator. When we put the ice into the ice box, no heat goes out and no heat comes in. These are some of the applications. Thank you.
Hello friends, myself Jithin Joshy. So far we have discussed about the various thermodynamic processes such as isobaric process and adiabatic process. Now we are going to deal with isochoric process. An isochoric process is a thermodynamic process taking place at constant volume. This process is also called as an isometric process or constant volume process. In an isochoric process, the final volume and the initial volume are same. That is, Vf is equal to Vi. It is because the change in volume dV is equal to 0. The work done in isochoric process is 0. So, the change in the heat applied is equal to the change in internal energy. That is, dQ is equal to du. Moving to the PV diagram, the 2 points marked I and F are the initial and final volumes. Since the volume is constant, we can say that Vf is equal to Vi. So, dV is equal to 0. The work done is equal to P dV. Since we have two states, that is the volume 1 and volume 2, we had to use integration. So W is equal to integral V1 to V2 P dV. We know that V1 is equal to V2. So the change in volume dV is equal to 0. So the work becomes 0. In graphical explanation, if we start from I to F, the volume remains constant, but the pressure P increases. Here, the work done is 0. Why it is 0? From the PV diagram, the work done is the area under the curve, but this curve is purely vertical, so no area. That is, the area is 0. It means the work is also 0. Using coal gas plus air mixture as fuel. Otto engine describes how the heat engine turns gasoline into motion. Like other thermodynamic cycles, this cycle turns chemical energy into thermal energy and then into motion. With this, I conclude my part for the presentation on the topic isochoric process. Thank you.
Now, I'm going to discuss about isothermal process, a very familiar but an important process. What is actually an isothermal process? It is a thermodynamic process that takes place at constant temperature. Whatever happens, temperature remains constant. So, in other words, we can say that there is no change in temperature or delta T is equal to 0. You can see a lot of examples regarding this isothermal process. The very best example is boiling of water. Whenever we boil water, we supply and heat. It is actually an external supplier. So the heat supplied is used to break the bonds and to change the state from liquid to the vapor state. And there is no change in the temperature. Now coming to the work done, we know the ideal gas equation is PV is equal to RT and the work done equation is integral V1 to V2 P dV. So substituting for P from the ideal gas equation, we can write it as integral RT by V dV. Integrating, we will be getting W is equal to nRT log V2 by V1, or in terms of pressure, we can write it as nRT log P1 by P2. So this is how we find the work done for an isothermal process. Now coming to the PV diagram, we know PV is equal to RT, temperature is constant, hence we can write PV is equal to a constant, or in other words, we can write it as P is inversely proportional to V. Hence, if we plot a graph, it looks like this. Here A and B are the 2 points and A is the initial condition and B is the final condition. And we must note that here the pressure and volume are the only that changes. Now coming to the applications of isothermal process, the first application is heat engine. Heat engine, they convert heat energy into mechanical energy. There is a source and a sink. Source is kept at high temperature while sink is kept at lower temperature.
When the cylinder with the working substance is placed on source, the pressure and volume of the gas changes, but the temperature doesn't change due to the infinite thermal capacity of the source. This is isothermal expansion. In the same way, there is isothermal compression in which pressure and as well as volume changes, but no temperature change due to the infinite thermal capacity of the sink. And the second example is change of state of liquids that I have mentioned earlier, that if we just boil water, what happens is that the heat applied is used to break the bonds of the water in such a way it changes to water vapor state. There is no change in the kinetic energy. Hence, there is no change in the temperature. And the third application is refrigerator. Refrigerator is an example of a perfect isothermal machine in which there is heat exchange is possible, but the temperature remains constant throughout. Now we have come to the end of the PowerPoint, and these are the certain references, or these are the certain sources from which we have taken our information. And the first one is Baiju's website. Second one is Understanding Thermodynamics by H.C. Van Ness. Third one is NASA website. And the fourth one is Heat Thermodynamics and Statistical Physics by S. Chand. Coming to the concluding part, we all know that thermodynamics, it plays a very important role in our day-to-day life, and it can be applied to various fields also. So it's my immense pleasure to thank Professor Dr. Pius Augustine for giving us this opportunity, and also to each of our group members to make this presentation worthy. Thank you viewers for being with us all this time. Thank you so much.